Okay, so I'm going to talk a little bit more about the low WIMP mass region and modulation analysis. So this has been the source of heated debate the last few years and still is. So it's worth talking a little bit about it a little bit more. So let me start with this plot that Peter showed already and summarize well the current state of confusion. So here it shows the WIMP nuclear cross-section in function of the WIMP mass. So the first thing to notice is that the sensitivity is quite lower than for high mass WIMP. That's because we are closer to the experimental threshold, and so thus the analysis is much more complicated. There's more background, more systematic errors, etc. So the second thing to point out is that we're looking at the tail of the halo velocity distribution. So the dependence of the model is it's bigger. So you can see here again the tension between the experiment, for example, gamma modulation being basically ruled out by most of the experiment, as well as cogent being ruled out by Xenon 100, and then CDMS that I will talk a little bit now. So here's the, you've probably seen already the modulation from gamma in between the 2 and 5 keV. So clearly that's a really nice summer-winter modulation, so there's no question. They're using sodium iodide crystal, 250 kilogram. They cannot discriminate the nuclear recall over the electron recall background. So what you see here is a small signal over a large background. And then they claim that's an evidence for a dark matter signal. So Peter already talked a little bit how we can reconcile this result with the other experiment. So I'm not going to go too much in detail, but first of all, of course, we can modify the halo model. But by itself, it's still difficult to, you can move the contour around, but it's still really difficult to make it compatible with the CDMS and Xenon result. So other explanation that has been discussed already is that it could be material-dependent scattering cross-section, and that could turn off, for example, the Xenon experiment channeling, which is, has been shown to be negligible. But I think most of the community believe that it could be something instrumental that will make this, this modulation. The bottom line is that we need to reproduce the gamma result. And so there are some experiments, such as the DMIs, that started to, they have a prototype already in the South Pole. So that's really nice. And then there's other experiments at Borexino and ICE, and then also in Korea, KIMS, which, however, are using cesium scintillator. But they show already a discrepancy with the gamma result. And here you can see some result from KIMS. But that's a lot more difficult to actually interpret because they have a different crystal. So here's cogent. They're using germanium crystal, so that it's a lot more easier to actually compare with CDMS. They only measure the ionization, so they cannot discriminate between nuclear recall and electron recall, such as CDMS. But they have a very low threshold, 400 eV. And you can see here the various neutron-activated peak, such as the 1.3 keV. So they have a really good resolution. So here's their results. So they see an excess at low energy. You can see here the spectrum that seems to fit be compatible with a WIMP interpretation, but really with not a big statistical significance. But you can see here this huge modulation in between 0.5 and 3 keV, quite much bigger than the one from gamma. But recently, it has been shown that most of the excess events are surface events that cannot be removed by any kind of phonon timing cut. That's based on simulation. And there are also some groups that show that first of all, they cannot separate surface from bulk, and they only quote upper limit. They all use also the same point contact detector. And we'll have also more results from different experiments using exactly the same setup. So that will be interesting. So let me now go to the CDMS experiment. So we are using a germanium crystal, and we detect both the charge and atomic phonons. So we did run the CDMS2 detector until September 2008, and we had several results, in particular high threshold, high mass WIMPs, but also in the low threshold. So here you can see a plot of the low threshold analysis. This shows the ionization yield, which is the ratio of the ionization over the recall energy in function of the recall energy. So you can see different type of event. This is the bulk electron recall. Some surface events which have incomplete charge collection because the charge drift to the wrong electrode, and they have a lower yield, which can then leak into the signal region, which is the nuclear recall band here. And in red, you actually see neutrons that produce this. You can see the band through using a neutron from a Californium source. You can see also another type of event we call zero charge events. So these events are mainly at the edge of the detector, and we don't collect the charge, but however, they have a good phonon signal. And this is, so we think that it's, so we have measured actually it's through extrapolation, that is actually the main background at low threshold. And then some from the result from the analysis show that all the events were all compatible with background event, mostly from zero charge events, so we didn't claim any signal. So that was done using the best 8 germanium detector. We also did some modulation analysis in between 5 and 11.9 keV. We didn't see any significant annual modulation, and you can see here the rate in function of the time. In blue, that's the CDMS modulation, or CDMS rate. And then you can see in red, sorry, the cogent modulation. So 5 keV is actually correspond to around 1.2 keV for cogent. So we probe a large part of the energy range of cogent, but not quite everything. So of course, that has triggered a lot of discussion. But we are currently doing the analysis to lower the threshold. This is a lot more difficult, so we're still analyzing, but it's going to be, we're going to have results soon, so that's exciting. So that's going to probe even more the cogent result. So we also released, as Peter mentioned, some results from the silicon detector, CDMS2. Here's a plot showing the efficiency of the blind analysis. Mostly, the efficiency is mostly decreased by the phonon timing cut, which is used to reject surface event. So here you see that some bumps here. That's because we optimize the phonon timing in different energy bins. So we estimate the background to be 0.47, and then the estimated background from the neutron was 0.13. Here's a plot you saw earlier showing the ionization yield versus recall energy. Here again, the bulk electron recall and some surface events. So this is, and then the different color is because of just showing the different energy bins. This is before the timing cut. And then applying the timing cut, we left with these 3 events really near the charge threshold. And then you can see again these 3 events, but this time in function, the yield, but in function of the timing parameter, and you can see that they well look like nuclear recall. So what can we say about these 3 events? Well, first of all, we can set a limit, which is by itself already incompatible with the DAMA result, but also a profile likelihood analysis showed that it's the WIMP plus background hypothesis so it favors a WIMP plus background hypothesis over a background only hypothesis as a 3.3 sigma level. So this does not rise as a discovery, but it does call further investigation, and we may actually be running in the future silicon detector. So What's coming next? So we're still going to continue analyzing the silicon to lower the threshold, improve our understanding of these events and the background, etc. We're also doing some analysis to repeat. So Juan Kohler from Cogent did some analysis of the CDMS2 detector and found some signal. However, we believe he was using the wrong background, and we're repeating this analysis. But what's coming next is actually we've been running since 2011 the super CDMS detector. You can see a schematic here. The difference is that it's a little bit larger, first of all, 1 inch. But also we have the phonon and charge readout on both sides of the detector instead of on just one side as CDMS2. This allows us to actually discriminate surface events using the partition, the phonon and charge partition. You can see here the ionization yield in function of the charge partition. So here on side 1, we had a LED source which create surface events, and you can see the loss of yield, so decreased yield, but it's well separated from the neutron nuclear recoil here. And it's a huge improvement in terms of surface event discrimination compared to the timing parameter that we have from CDMS2. So that's very, very good. And also the phonons, we can use it. And you can see here surface events and a phonon pulse on the side 1, where it is the surface events, and then in red in the other side. So there's a big difference. Here is just a bulk event, and it shows exactly the same. So this is very good because that will allow us also, because the signal to noise of the phonons are very good at low energy, we can then discriminate much better than CDMS2, some events like the zero charge events, etc. So that will be really useful. We have been also using the same, one of the detector in a slightly different mode, modify it so that we actually can increase the electric field. And that amplify the phonon, because when the charge drift, they produce this phonon called negative loop phonons. So that's really amplified the phonon signal. To give you an estimate, we did run at the voltage of 69 volts, and then that increased the phonon signal by 24 instead of like 2 or 3. But that was in the extent of not having a discrimination, electron recoil, nuclear recoil in this particular case. But that's really lowered the threshold to a really good, to 100 eV. And then we are finalizing this analysis, and there's going to be some result in a few weeks. So to summarize the super CDMS Sudan, so we're going to have, so again, this plot showing the WIMP nuclear cross-section in function of the WIMP mass. So both the super CDMS low threshold analysis and this CDMS light with amplified phonon signal will further probe this region here. So that should be really interesting, and we're looking forward to unblind the data. It's still blind, so I cannot say anything, but that's really interesting, and we should all be looking forward. So that's going to be probe more and test more this low mass WIMP region. We can look even further, and maybe we can actually even get a much better resolution on the phonons, because if you look at this plot, it shows the phonon resolution in function of the critical temperature of the TS sensor, tungsten sensor, for different TS design. But the bottom line is that it depends on the critical temperature, and then we can eventually, we've been running at 60 millik or 50 millik, but we can improve by a lot the resolution by decreasing the critical temperature. But that means that it will make it much harder to have a cryostat that goes to that low temperature, and then maybe some systematics. But we can dream of having, for example, a single electron hole spectrum where we have each electron hole that makes a discrete spectrum here when we amplify it also with like a large electric field. So let me finish here by this plot that Peter showed already. So Super CDMS Sudan is going to further probe this region, but what really will clarify the entire region is this Super CDMS Snow Lab. So we're going to have a much lower, first of all, ionization resolution to 100 eV using some a new readout amplifier HEMT, but also lower phonon resolution. And then that should really, really clarify the entire region here. So that should be interesting. So hopefully in the next few years. But other experiment that will also probe this region, for example, Lux and so on, that might be interesting as well in the next year. So yeah, that's my conclusion. So still lots of confusion in this low mass WIMP region. So definitely we'll need more data. We need to lower the threshold. So we're going to have some new results from Super CDMS. Also, there's going to be some experiment that will directly check the gamma modulation using exactly the same crystal in South Pole, for example. So that will be interesting. And then Super CDMS Snow Lab is well suited to actually investigate this low mass WIMP region with the TS sensor, which can have a really, really good phonon threshold. Yeah, that's it.
You didn't say anything about DOMIC, the role that it might play.
Yeah, so I'm not exactly sure. Maybe someone else knows better about DOMIC, but yeah, I mean, that's one of the experiments that also should be interesting to watch. But I don't think I have.
I mean, right now it isn't as sensitive as
Yeah.
some of the most sensitive experiments, but okay.
Yeah, sorry about that, but.
And I was just wondering how you imagine that this low mass scenario is going to get resolved. I mean, I guess you sort of said it, but.
I mean, for me, I think that's really going to be solved by Super CDMS Snow Lab, because it has a really, it's probed like the entire region. So that should be like really, really powerful in terms of clarifying the entire region. So I mean, we can expect some result already using Lux, for example. But as you can see, the expected limit is going into this region here. So that will depend. They have a much better light efficiency than Xenon 100, so they should be much better. And from some study, if there's a signal here, they should, from Van Hooper, I think he estimated that it will be like between 4 and 20 events in Lux. So that will be, of course, interesting to watch in the next year.
So if you continue to rule out a signal, say with Super CDMS, you still won't know why DAMA is saying. I mean, they had a paper on the archive, I think a week ago, where there's, even stronger. They say nobody can explain our backgrounds. It is dark matter. It seems like you just need something like DM ice. You need the same material down at the South Pole. You really want to know what's causing this modulation, right? Because it's really real. So just ruling it out with other materials won't ever explain that,
yeah.
I guess.
Unless you find some signal, but. I was more like optimistic, maybe. But you're right. I mean, we need the same thing, and then we need exactly the same crystal. And the EMS might be really nice to, yeah. Clearly, that's going to help in terms of understanding. So, I mean, there's like high hope that in the next few years we'll understand what's going on. I mean, we might not understand why the, gamma had a modulation, but at least there will be good cross checks.